Hello friends, hope all of you are well. So today we will start with our sequence of function lecture 3. So here in this topic I will discuss the some properties that we can see in the sequence of function. That is the consequences of the continuity, the boundedness of the sequence of function along with the limit function. Okay, so first of all I want to say that if you are new at my channel, then please go and subscribe the channel and share with all of your friends. Okay, so let us start with our lecture. So in our previous lecture I have given a problem to all of you to check the uniform convergence of the sequence of function fn. So here this problem is very important because this problem has repeated so many times in the exams. Okay, so many of you have asked me how I am writing limit n tends to infinity fnx equals to 0. That is how I am saying that the sequence of function is pointwise convergent and converges to the point 0. So here I want to say more another thing. In my previous lecture note there was a mistake, and please rectify that. Here whenever in the second term, whenever you put the supremum, then the term will be 0, but the result will not differ, the result is same, but in the previous lecture it was miswritten. Okay, so let us start with the thing that how we are getting the limit function of this sequence of function is 0. Okay, so how it becomes 0? So you can see whenever we put x equals to 1, then the sequence of function automatically converges to 0. Okay, and if you put x equals to 0, then the sequence of function becomes a 0 function which converges also to the point 0. So for x equals to 0, sequence of function converges to 0, and for x equals to 1 it becomes a constant sequence again, that is 0 0 0, which again converges to 0. Now if you choose any value in between 0 and 1, then what will happen? So if I say that x is a point between 0 and 1, then we can apply the Archimedean property of the real number. So what is the Archimedean property of the real number? That is for any positive quantity x or y, then we have a natural number n such that ny greater than x. So we are simply applying that logic here, that we are finding a natural number p which is greater than 2 such that we can write down pc is greater than 2. Okay, so if pc is greater than 2, then simply we can see 0 less than 2 by p less than c. So think about that. If any natural number which is greater than or equal to p that crosses p, obviously satisfying this inequality, so we can say that 2 by n less than c will hold for each and every natural number greater equal to p. Why? If n greater equal to p, then 1 by n less equals to p, that I have written here. So 2 by n less equals to 2 by p. So 2 by n less than c less than 1, because c is already in this interval 0 to 1. So we can see what? That is c crosses 2 by n. Whenever c lies between 0 and 1, for each and every term if you choose, then there must exist a natural number such that c will crosses 2 by n. So if we go to the definition of the sequence of function, then we can see whenever x crosses 2 by n, the sequence of function automatically comes to the point 0. So it again becomes a 0 function. So c crosses 2 by n, so for each and every n greater equals to the natural number p, fnc will automatically become 0, or we can say if pc is 0. So in the next line we can write down if nc equals to 0 for each and every n greater equals to p. So the sequence of function pointwise convergent and converges to the point 0 for each and every natural number which is greater equal to 2. And what is that 2? P is nothing but p is a natural number which is greater than 2. So we are mentioning it here. Okay, now you can understand this problem. You practice, because this problem is repeated so many times. Okay, now let us go for our next topic. The first thing is that today we will learn what is the uniform norm. So what is the uniform norm? Uniform norm is nothing but, say we have a set capital A which is a subset of set of all real number, and we will define a function from the set to the set of a real number. Then the function is said to be bounded and is said to have a bounded norm or uniform norm if we can say that phi norm of phi over the set A is equals to supremum of phi x belongs to A. Whenever this case exists, only when that phi A becomes a bounded subset of R. So all of you know, whenever the function and its range set becomes a bounded subset, then we can say the function is automatically bounded. So for any bounded function, we have the uniform norm. That is, for each and every x belongs to A, we will take mod of phi x and we will find out the supremum of this quantity. So we will automatically obtain the supremum or the uniform norm of the function phi. So you can observe from here that if I am choosing epsilon greater than 0 and I am say that a phi is the uniform norm of phi is less than epsilon, so if the supremum is less than epsilon, then each and every function and modulus of that function must be less than epsilon. Because supremum is less than epsilon, then it implies mod of phi x is automatically less than epsilon for each and every x belongs to A. So with this definition of the uniform norm, the Mn test can also be stated as follows. That is, a sequence of function fn, which is a sequence of bounded functions on the sub A subset of R, converges uniformly on A to a limit function f if and only if the supremum or the uniform norm fn minus f tends to 0 over the set capital A on which we have defined the sequence of function. Okay, the proof is immediate and proof is same as we have done in the Mn test. So in exam, if this statement is given, then no need to worry, just follow the theorem that we have done in the previous lecture. Okay, so let us start with one of the consequence of the sequence of function, that is the boundedness of sequence of function and its effect on the limit function. Okay, so the theorem, what is the statement of the theorem? Let us start first understand. Say we have a set capital A which is a subset of set of a real number R, and for each n belongs to natural number, fn A to R is a sequence of function given, where each and every function is nothing but a bounded function on the set capital A. Then if thus it is given that sequence of function fn is uniformly convergent, if it is uniformly convergent on the set capital A, then the limit function f is automatically bounded on capital A. That we have to show. Okay, it is one of the most important property. So let us prove it. So first of all, we will just write down the definition of the uniform convergence of a sequence of function. All of you know that if a sequence of function is uniformly convergent on the set capital A to a limit function f, then for any positive epsilon greater than 0, we have a natural number which is solely depending on epsilon, such that fn x minus fx will be less than epsilon for each and every n greater equal to k. Okay, now it is given in the question that fn is bounded for each and every n, the function is bounded. Okay, that is, each and every function in the sequence of function is a bounded function. So what is the definition of a bounded function? For a bounded function, we obviously have a positive real number m, such that we can say that mod of fn x should be less than m for each and every x belongs to capital A. And since it is given that is for each fn is bounded, so for each n, obviously fn x less than m for all x belongs to A. Now we know from this inequality that that is mod of fx minus mod of fn x, this quantity is obviously less equals to mod of fx minus fn x. Okay, this is the inequality that we already know. So from this inequality, we can simply write down it as mod of fx should be less equal to mod of fn x plus mod of fx minus fn x. We can write down it as like this way. Now you can see that mod of fn x minus fx is already less than epsilon, and for each n, mod of fn x is less than m for every x belongs to the set capital A. So if we substitute these two values here, then we can see that mod of fx less than m plus epsilon. Now you can choose any epsilon, and then still the function mod of fx is less than a fixed positive real number. So we can say that the function fx is a bounded function. Okay, so always remember that if a sequence of function is uniformly convergent and each function in the sequence of function is bounded, then the limit function is automatically bounded. Okay, so let us go for some note. So the note are also important that I want to say. From this theorem, if it is given in the question that is the theorem is true that if the sequence of function is pointwise convergent. No, we cannot declare it, because if a sequence of function is pointwise convergent on A, then it is not guaranteed that the limit function is also bounded wherever each and every term of the sequence of function is bounded. So let us try to cite an example. So let us consider for each n, fn is closed interval 0 open 1 to real number is defined by this function 1 plus x to the power n minus 1. X belongs to closed 0 open 1. So obviously you can see here that this term is nothing but gives us a remembrance of the GP series. So if we expand this term as a plus up to infinity, then obviously we will get a geometric progression series. So whenever you take limit n tends to infinity, whenever x belongs to close 0 1, the limit of this function automatically become 1 plus x square plus dot dot, which is nothing but 1 minus x to the power minus 1, or we can say 1 by 1 minus x. So automatically you can see that this function is not a bounded function on the closed 0 open 1. Why? Because it is a infinite series 1 plus x square plus dot dot, which becomes unbounded, wherever if you take the modulus of fnx, it becomes 1 plus x to the power n, and here we have finite number of terms, so this is less equals to 1 plus mod x plus mod of x to the power n minus 1. Here we have applied the triangle inequality. So whenever x lies between close 0 open 1, if you substitute the highest value of x, that is 1, then each and every term will be less than 1. So the sum of this term will be less than n. N is nothing but a fixed positive natural number. Okay, so for each and every n, mod of fnx is less than n for all x belongs to close 0 open 1. So each and every term of the sequence of function is bounded, though the limit function is not bounded here. Now let us go for another note. That is, the note says that if the sequence of function is bounded for each and every n, and the sequence of function is uniformly convergent to the limit function f, then that statement that we have done in the theorem says the sufficient condition for the boundedness of the function f, but not the necessary condition. Why? Because of the fact that it may be seen in some example that the sequence of function is not uniformly convergent, though each and every term of the sequence of function is bounded, wherever the limit function is also bounded. So if the limit function is bounded, you cannot guarantee that the sequence of function is always convergent uniformly. Okay, so herever we are citing the example again. I have already declared this is the most important example, and we will take this example in various problems to cite some contradictions. Okay, so here we have considered fnx equals to nx by 1 plus n square x square in the closed interval 0 1. Here you can see that each and every fnx is bounded over the interval closed interval 0 1, and you know that the limit function f is equal to 0, fx equals to 0 for all x belongs to closed interval 0 1, which is a constant function. That means it is automatically bounded. But we have already proved by MN test that the sequence of function is not uniformly convergent on closed interval 0 1. Okay, so let us go for our next theorem, the continuity. It is as important as we have learned the boundedness of the sequence of function, but this is the one of the most important theorem in this chapter, because with the help of this theorem we can very easily check the uniform convergence of a sequence of function. So let us start with the definition of the statement of the theorem. So the statement is like same, that is, if we are considering a set A which is subset of set of a real number, and for each and every n belongs to natural number, each fn a to r is a continuous function on A. Now if sequence of function fn is uniformly convergent on the set capital A to a limit function f, then the limit function f is automatically continuous on the set capital A. So this means that if the sequence of function fn is uniformly convergent on a set capital A, and where each and every term of the sequence of function is continuous function, also the limit function we have in our hand, and if the convergence is nothing but a uniform convergence, then the limit function becomes automatically continuous on the set capital A. So let us start with the proof. So what is the proof? Simply we have first written the uniform convergence of the sequence of function. That is, for uniform convergence we have a pre-assigned epsilon, for which we have a natural number k, such that mod of fnx minus fx is less than epsilon by 3 for each and every n greater equals to k. Okay, so here we can see from k and onwards this inequality is getting satisfied. From k and onwards this inequality is getting satisfied. That means in place of n, if you put k, still this inequality will be satisfied. So fkx minus fx is also less than epsilon by 3 for each x belongs to A. Since a condition is given here that each and every term of the sequence of function is a continuous function, so we can say that fkx is also a continuous function. Okay, so if each and every fn is continuous on A, then fk is also continuous at x equal to c, which belongs to A. Now think about that. In inequality 1 we have stated that this inequality holds for each and every x belongs to A. So if you put any specific element c from capital A to this inequality, the inequality will again be satisfied. So mod of fkc minus fc will be less than epsilon by 3 again. Okay, now we are going to check the continuity definition. So again I am saying the same thing, that is, each and every term fn is continuous on A, therefore fk is also continuous at x equals to c, because x equals to c is a member of capital A. So let us apply the definition of the continuity. The definition of the continuity says that for epsilon greater than 0 there exists a delta greater than 0, such that we have mod of fkx minus fkc should be less than epsilon by 3 for x belongs to neighborhood of c comma delta intersection A. That is the definition. All of you know that is the definition for the continuity. Okay, now what we have to show? We have to show that whether the function is continuous on A or not, that is the limit function. Okay, so to check the continuity of the limit function, we are simply taking the difference of fx minus fc. If we can say this difference is less than epsilon for x belongs to neighborhood of c comma delta intersection A, then we can declare that the function is continuous at x equal to c. So we are applying the triangle inequality here. So now think about that mod of fx minus fc. Can we write down it as mod of fx minus fkx plus fkx minus fkc plus fkc minus fc? So whenever we break it into the triangle inequality, we have these three terms, that is mod of fx minus fkx plus mod of fkx minus fkc plus mod of fkc minus fc. Now by 1, 2 and 3, all these three terms are less than epsilon by 3. So these three terms are less than epsilon by 3 for what? for what value of x? X belongs to neighborhood of c comma delta intersection a that we have declared in number 3. So we are writing this. So what we can see here, that is mod of fx minus fc is less than epsilon for each and every x belongs to this neighborhood. So we can declare that the function is continuous at x equal to c. Hence we can say the function is continuous on x equals to a, because c is nothing but a arbitrary point. Now let us discuss some notes along with this theorem. So the first note says that, again similar as the boundedness theorem, that if a sequence of function is pointwise convergent on a set capital A, it is not guaranteed that the limit function is always continuous function. So for this we are considering the example x to the power n minus 1. Here you can see that for x equals to 0 the function converges to 0, there is a sequence of function converges to 0. For 0 less than 1 it also converges to 0, but for x equals to 1 sequence of function converges to 1. So fx becomes 0 and 1. So obviously you can see the function is not continuous at x equals to 1. So the limit function is not continuous. Now the note number 2 says that, again, that the condition we have learned in the above theorem is the sufficient condition for the continuity of fx. That is, it may happen, but it is not the necessary condition. That is, it may happen that each and every term of the sequence of function is continuous. Also the limit function is continuous, though the sequence of function is not getting uniformly convergent on the set capital A. How? Consider the same example that we have taken for the boundedness theorem. Okay, so here we can see that each and every term is nothing but a continuous function, represents some continuous function. Also fx equals to 0 represent the constant function which is always continuous. So each and every term of the sequence of function is continuous. The limit function f is also continuous, though the uniform convergence is not getting here because the sequence of function is not getting uniformly convergent. Now let us go for the point number 3, note number 3, and it is the most important note for this theorem. Since we are saying that each term of the sequence of function is continuous, then also if the sequence of function converges uniformly to the limit function f, then the limit function f is also continuous. That is the statement we have learned in the previous theorem. But what will be the contrapositive statement of this theorem? So if we think about very clearly, the contrapositive statement will be like this, that if the limit function f is not getting continuous, then we can directly say the sequence of function is not uniformly convergent. If the sequence of function uniformly convergent, then the limit function automatically becomes continuous, for each and every term is continuous in the sequence of function. But if the limit function is not continuous, then we can directly say that the sequence of function is not uniformly convergent on A. But if it happen that we have an example just like note number 2, that each and every term of the sequence of function is continuous, also the limit function is continuous, then we cannot guarantee that always the sequence of function is uniformly convergent. But if the limit function is not continuous, then we can guarantee the convergence will not be uniform. So let us go for some examples. These examples we have done several times. So here we can see the limit function becomes 0 and 1, which is discontinuous at x equals to 1. So we directly say the limit function is not getting uniformly is not continuous, therefore the sequence of function is not getting uniformly convergent. Let us go for the another problem similar as our last problem, 1 minus nx, 0 less equals to x less equals to 1 by n less than x less equals to 1. So for x equals to 1, the sequence of function converges to 0. For x equals to 0, it converges to 1. Two different points have already arisen. But if x lies between 0 and 1, then by Archimedean property we have a natural number m such that 0 less than 1 by m less than c, that we have done in the previous problem. So we can declare for each and every n greater equal to 1 by m, 0 less than 1 by n less than c. The inequality will be satisfied for each and every n greater equal to m. So whenever c is getting crosses over 1 by n, the function converges to 0. So fmc will become 0 because c is getting 1 greater than 1 by m. So this will imply f and c is automatically 0 for each and every n greater equal to 1 by m. So as limit n tends to infinity, n becomes larger and larger, the limit function, the limit of this sequence becomes automatically 0. So it converges to two different points and the limit function becomes different quantity. So it is also discontinuous at x equal to 0. Therefore the convergence is not uniform. Now the same type of problem is given here. You can check it and you can solve it by yourself. Okay. Now go for another problem. Another two problems are given here. Similar type of problem. Go and check it and solve it. Okay. And the last problem is that one of the most important problem in this context. A function phi is a continuous function on closed interval 0, 1, and for each n belongs to natural number, it is given fnx equals to x to the power n into phi x. We have to check the necessary and sufficient condition for the convergence, uniform convergence of the sequence of function fn. So first of all, how we get the uniform convergence criteria? Simply we have to check the pointwise convergent. According to the pointwise convergent, we have get some condition on the function phi. So you can see here, for 0 less equals to x less than 1, the limit of the sequence of function becomes 0. But at x equals to 1, sequence converges to phi of 1. Okay, sequence converges to phi of 1. So the limit function becomes fx equals to 0 for 0 less equals to x less than 1, and at x equal to 1 it becomes phi of 1. Now all of you know, to uniform convergence of sequence of function means that if the each and every term of the sequence of function is already continuous, then the limit function must be continuous, otherwise it will not uniform convergent. So phi of 1 must be equal to 0. Then the limit become a constant limit, that is 0, and then we can declare that it will be uniformly convergent. It becomes the necessary condition. But what will be the sufficient condition? To considering phi 1 equal to 0, we have simply checked here how it converges uniformly. Because for phi 1 equal to 0, we can see the sequence of function fn at x equal to 1 converges to 0. And for the rest of the portion, it converges automatically to 0. So the limit function automatically becomes 0 function. So we have applied the Mn test here, and for Mn test we can see that each and every fn is continuous over the closed and bounded interval, closed interval 0, 1. So if a function is continuous on a closed and bounded interval, then the function becomes automatically bounded, that we have written here. And if a function is bounded over the closed and bounded interval, then it has the supremum inside the closed and bounded interval. Now here phi of 1 equal to 0, so we are considering any point in between close 0 open 1 at which the supremum of mod of fn exists. So we are considering a point x equal to a lies between close 0 open 1 at which we are considering the mod of fn will attain its supremum value. So what will be our Mn? Mn will be equal to a to the power n phi of a, because we are considering x equal to a in between close 0, 1. Why we are not considering x equal to 1? Because at x equal to 1, phi 1 equal to 0. So the Mn automatically becomes 0. So we are considering the general case. At x equal to a between 0 and 1, Mn will be equal to a to the power n phi of a. Now you can see that whenever a is lie between 0 and 1, automatically its limit becomes 0, and phi a is nothing but a constant and it is bounded. Therefore sequence of function fn converges uniformly on the closed interval 0, 1. So what is the necessary and sufficient condition? The necessary and sufficient condition will be phi of 1 equal to 0. So try to solve all the problems. Okay.